Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, I'm Madan Muswati from the Software Reliability and Research Group, and it's my pleasure to invite Greta Yosh from Tel Aviv University. She's working with Muli Sagiv and Alexander Rabinovich, working on various aspects of reasoning about heap manipulating programs, and today she's going to be talking about employing decision procedures for automatic analysis and verification of heap manipulating programs. Wow.
Thanks, Madan. So, good afternoon, I suppose. This is the title of my thesis going to be. In my thesis research, I developed techniques for combining automatic program analysis with decision procedures. I'll talk louder.
Yes, if you can move the microphone up to your color, maybe. Closer.
Okay. Is it better? Maybe it's off? I'll try to speak louder, and maybe it works. So in my thesis research, I developed techniques for combining automatic program analysis with decision procedures for validity and satisfiability of logical formulas. And I apply these techniques to heap manipulating programs. Now, there are several exciting applications of this, and I'm going to talk about some of them. So first, this is the setting in which I explored my techniques. Programs written in imperative programming languages, C, C++, Java, and such. And I'd like to reason about properties of such programs. And these properties can be roughly divided into three classes. The first one, cleanest properties, such as absence of null dereferences, absence of runtime exceptions. These are usually not program-specific. These usually come with a definition of the programming language, such as a program should not access memory that is not allocated to it. The second kind of properties are program-specific invariants, such as class invariants or object invariants, or data structure-specific invariants. For example, the data structure is always acyclic. We often need to reason about this kind of invariance in order to prove cleanest properties and show that program doesn't crash. But, well, even if program doesn't crash, it might not be doing what we want. So the third kind of properties we can use to define the expected functionality of the program, such as specify the result of a procedure using its inputs, pre- and post conditions for procedures, and so on. So we would like to be able to prove these kind of properties automatically, but it's well known that even very simple properties, proving very simple properties of programs is undecidable for programs that anybody cares about. So there are two approaches in general. One is to use abstraction to over-approximate program behavior and then reason about the over-approximation. And the other one is to ask the user for help. So in the first approach, there are usually like three steps at the high level. One is to choose an abstract domain in which every element represents a set of concrete program states. Then find a finite set of abstract values which over-approximate all possible reachable states, and then check the property over the abstract values. This technique, the abstract interpretation machinery, provides us with these advantages that, first of all, we don't need to specify loop invariants. We only need to choose the abstract domain, basically. And the second advantage is that if we manage to prove the property over the abstract states, that we know it holds for all reachable program states. However, if we fail to prove the property, it doesn't mean that it's not satisfied by the program. It just means that maybe our abstraction is not precise enough. So we can come up with a more precise abstraction maybe. And there is, of course, the trade-off. If the abstraction is more precise, it costs us more to run the analysis. The second approach, the deductive verification approach, says, okay, we have we specified various parts of the code with precondition, postcondition, loop invariants, and now we can automatically generate verification condition formulas such that if the formula is valid, then we know that the program complies with the specification. And we can check validity using different tools, either automatic or interactive proof assistant or manually. We can find different ways. And the advantage of this approach is that we can write very expressive specifications, and then if the user is smart enough, he might be able to prove. And we can use various tools to help us with the proof. Now, basically, the advantage of abstract interpretation is that it provides some automation, and the advantage of the classical approach is that it's expressivity, and which basically comes with the ability to write specifications and to ask the user for help in the proof. So what I would like to do is to take this ability and add it to the automatic approach and make automatic approach more sensitive to specifications and leverage the specifications for doing various tasks. For example, we can use the insight that the user is willing to give us in order to improve the precision of the analysis. Also, certain operations are much easier to perform on specifications than on abstract values, such as we can take conjunction, easily specifications or logical formulas, and so on. And other operations are much easier on abstract values. For example, join or widening, that's the purpose of abstraction. So we want to do the specifications which are easier on abstract values, to do it using the standard abstract interpretation tools, and then use specifications when these provide us with benefits. And there are several applications. The first one, for example, is extracting information from abstract values. So we computed some set of finite abstract values which represents the behavior of the program. And now we want to ask queries about these values, which, for example, queries that we didn't mean originally when we designed the abstractions. And often it happens that the information is there, it's just that we have no tools to query the abstract values. Another application of this first bullet here is just to check user-defined assertions in the program. It's easy to check these assertions if the abstract value encodes the information explicitly. But what if not? How to check assertions then? The second application, which I'm the most interested about, is modular analysis. The idea there is to analyze each procedure only once, using program analysis techniques, that is without loop invariant. And then the interaction that analyzed procedure has with other parts of the code needs to be specified somehow. So we need specifications together with program analysis to be able to do this kind of applications. Now, the next one is parametric abstractions, like predicate abstraction, in which the abstraction is actually not known at the time of the design of the analysis, and the specification of the abstractions is created on the fly in some way, so it can be seen as another way of using specifications. The last application is also, I think, very exciting. It speaks about different layers of abstraction in the program itself. So we have a client code and the library, and the client uses the library. Library is implemented using one data structure. The client doesn't need to know how the library is implemented. So there are different layers of abstraction in the program, and we would like to use different analysis maybe for each part of the program. That could be one of the applications of using specifications or specification language, which communicates from one analysis to another the information that is needed to prove the whole program. So there are several applications, and the question is how to incorporate specification into program analysis, which usually reasons about abstract values, not about formulas. So program analysis is not designed to take formulas into account. unless the abstract domain is the domain of formulas, which is rarely happens. Okay, so we need new operations. The question is, which operations do we need? We need some way to implement these operations. And also another question is, what are the requirements about the specification language that we are using that come from maybe this implementation, or which specification languages are good to be incorporated in program analysis? Yeah.
So when you say that the analysis is not designed to take specifications into account, it would have to take the Boolean expressions of the program into account, right? Like if guards of if statements and loops, and if the specifications are similar to those Boolean expressions, then wouldn't the program analysis already take the specifications into account? Or do you have something else in mind for the specifications?
So that could be one way to choose the specification language, to choose something which is also which is used in the program. But sometimes we want specifications which are more declarative, and then we maybe need a different language. And also another application that I have in mind is the reachability. So to implement something which, a specification which checks that every element in the list is sorted, you need to traverse the list, but maybe we can specify it in a different way using reachability. So everything that is reachable.
So do you assume that, for example, the specification language can state stronger invariance in general that is available in your abstraction?
Exactly. That's one of the difficulties in implementing these operations, and I'll talk about it.
Because, I mean, some languages actually goes the other way there. Some spec languages are so sort of limited or restricted that, you know, the abstract domain one has underneath it might actually be stronger, but you look at it the other way.
So there is there is a range of specification languages that differ in expressivity that we can choose. We can probably choose a specification language which can distinguish between everything that happens in the concrete world, or we can choose a specification language which is less precise than the concrete world, but not as abstract as the abstraction we are using. That's basically the range that these algorithms that I'm going to talk about allow. So the way I view it, you can ask the user to supply some specification, which is usually less precise than the concrete, than what happens in the concrete program. But you want the language to be expressive enough so the user can give all the information that he is willing to give you, and then deal with it in the best way you can. But there are other trade-offs. I'll talk about it more. So these are basically the questions that I'm trying to address. There are various other questions, but I want to concentrate on these. And as a motivating example for the first one, which operations we need, I'd like to consider the modular analysis approach. So here again we have this idea of analyzing each procedure in isolations from the others, where the hope is that if we analyze each procedure only once, and it's a small small code fragment, we can spend more resources on the analysis, using maybe more precise techniques than we can do for the whole program. That's the motivation for doing modular analysis. Now the difficulty is that interactions of the analyzed procedure with other procedures need to be specified somehow by a user or by maybe some other tool which infers specifications. So this approach in general requires specifications. And let me show just an example of how it works, and then we'll see which operations over the specifications we might need. So in this example, I take my usual example, implementation of a linked list, single linked list with this next field, and I have some method append for which the user gave me these pre and post conditions. The precondition says that the first list, which is an input to append, is acyclic, and it's disjoint from the second. And the post condition for append is some formula in some specification language. I'll talk about it later, which exactly specification language we can use. But the idea is that this formula relates the state after append was executed to the state before. In particular, it relates the information about the heap that we have after append executes to the heap before. And it includes also information such as mod or preserve in this post. So this talks about two states. For example, we can write post condition which says that for all objects in the heap, the n field remains the same after append, except for the last one, reachable from A, for which the next field is now pointing to B. Just this usual specification. Yes?
So three variables of that expression that you don't show explicitly are the pre-state of the heap, the post-state of the heap, and the result value.
I'll show the specification, the possible way to write this. I'll show later, and there we use different modeling. We use two vocabularies, but that would be another way to do it. Okay, so this is an example of a library code, and I have some client code or a test method which takes a list as an input, has some precondition, executes a loop, allocates some more things, and then makes two calls to append. And now I want to use program analysis techniques to do the analysis of this code. So the first thing to do is to create an abstract value. Oh, sorry, I forgot to say that what I want to verify here. Oh, it's good that I have these animations. What I want to verify here is that, for example, before the call to append, its precondition holds. And for example, I can also have some postcondition for the test method itself, such as that the return value is also acyclic, just as an example. And now suppose that we analyze this code. We start with some abstract value A0, which represents all states in which Z points to an acyclic list. And then the idea is to use usual program analysis technique to analyze this part of the code, including the loop, and it doesn't need loop invariance. And now we want to check this assertion over the abstract value A1. So this would be the first operation that we would like to implement, is assertion checking. And this assertion is not necessarily something which is obvious from the way the value A1 formed. Maybe it's implied, but not easily possible to read out from A1. And then suppose that this assertion holds, and in this program, if we use, for example, canonical abstraction, we'll be able to find out. Now we have this call to append, which we need to compute the effect for. And the idea is, instead of using the source code for append, to use the post condition that we have. So instead of analyzing this code, we want to use the post condition and some operation which takes this A1, the post condition, and returns a new abstract value A2. And now we want to check the next assertion on the value A2. Now, to be able to prove that this assertion holds for A2, we need the operation assumed to be precise enough so that the information that we had about, for example, Z being disjoint from X, the information that we had about the heap before the first call to append, to still be present here in A2, so that A2 is sufficiently precise to check the second assertion. So I would like to implement this operation, assume in the best way possible, extract as much information from the post condition of append as I need. Okay? And then continue the same way for the second call to append and check this assertion, and same things apply. Now, these are the operations these are examples of operations that I would like to have. And these are some more operations which are useful for other applications that I mentioned. So the first one, the assert, takes two inputs, abstract value and the formula, and it returns yes or no, whether all concrete states represented by A satisfy the formula. Now, assume operation also takes two inputs. One is from the usual abstract interpretation setting, and the other one is specification, and it returns a new abstract value. Now, in a sense, this is more difficult already because now here we need to compute some new abstract value, and we would like it to be precise to some definition, which will be clarified in a very close. And here we only need yes or no answer. So in a sense, this is already more difficult than assertion checking. Well, the other operations also combine abstract values and specifications. So this one takes an abstract value in domain A and returns an abstract value in domain B. Now, the question is, yeah?
So you're assuming that verification is done by some kind of forwards propagation, as opposed to doing backwards?
Yes. Forward direction, like in abstract interpretation, I have abstract transformer which goes forward. I could probably define it backwards as well. I could, yeah.
And T is an instruction in the program?
Well, in this example, T would be some program statement, and I want to compute the abstract effect on that, of that statement on A. Okay. It can be something more general. Okay, so these are the operations I'd like to implement. Now, let's look inside the box. So I can implement assert if I can take this abstract value, translate it to a formula, and then check implication of this formula and the assertion using a validity checker. So I can implement that if I have a box which takes an abstract value and returns a formula. I can also implement assume if I have two boxes, one which takes abstract value, returns a formula, just like the one we used here, and then take a conjunction of this with phi. So it will filter out from A all states that don't satisfy phi, and then take this formula and compute an abstract value for it. I can also implement Similarly, I can implement an abstract transformer, and I can also implement domain change using similar operations for the corresponding domains. So what I'm using here are two basic operations. One is called gamma hat, and the other one is called alpha hat. Gamma hat takes abstract value and returns a formula in the specification language I'm using, and alpha hat takes a formula and returns an abstract value. So these are the operations I'd like to implement, the basic operations. If I have those and the validity checker, I can implement all the things I talked about in this previous slide. Yeah.
So an alternative to the assertion assume would be that you apply alpha hat to phi, and then have an implication or checker within the abstract domain.
By applying alpha hat to phi, I actually lose information. I didn't define alpha hat precisely yet. It's just intuition.
So it will always be strictly weaker than.
Not always, but okay. Let me get to the definition of alpha hat. I hope it will be clear from there. It's just that it can lose information.
Yeah. So this is the strongest possible.
Yes, this is I suppose. Yeah. Up to some caveats apply, and I'll talk about it as well. Okay. So going back to this picture, once we added specifications, we also need the symbolic operations. And by symbolic here, I mean operation that involves both abstract value and specification. And we need a validity checker, which is kind of similar to what's going on the right-hand side. So that's the high-level picture of what's going on. And in my thesis, I developed two algorithms for implementing symbolic operations. I'll describe them here. In the work we did with Tom Ball and Muli, in the ISTA paper, we developed a technique which can also be used to reduce the cost of symbolic operations using concrete execution. I'm not going to talk about it here, but if somebody is interested, I can talk about it offline. So I did a case study in using these operations for modular analysis. And these operations use validity checkers, or satisfiability checkers. The case study taught us a lot of interesting things. It was in the setting of heap-manipulating programs. So for writing specifications or interesting specifications for these programs, we needed to reason about reachability between objects in the heap. And it's difficult to reason automatically about these kind of properties to check validity or satisfiability of formulas which involve transitive closure. It's very difficult. So in the second part of my thesis, I concentrated on specification languages for recursive data structures, such as linked lists, trees, and so on. And the requirement is that this specification language can express the properties that we want and at the same time can be useful for us for doing automatic program analysis, so that it has some reasoning tools available. It was difficult to find such language. We had mostly we had negative results until we came up with this logic called logic of reachable patterns, which is both decidable and very expressive, which is a kind of a combination, a good balance for reachability and other properties we need on one hand and decidability. And I'll talk about it today a little bit, not go into too many details. Recently, I did a work with Eran Yahav and Satish Chandra, which kind of related to both of these things. So the idea was to derive specifications for type state verification, to derive summaries for procedures in the context of type state abstraction. The interesting thing about this is that the problem itself was motivated by a real need. So there was an interprocedural analysis for type state, which worked pretty well. And when we tried to scale it, or when they tried to scale it, the problem was that the interprocedural analysis required too much space. So one way to reduce the space was to summarize some parts of the code and then use the summary instead of using the usual interprocedural technique, because the summary was much more concise than the table, than the summary table of IFDS. So this was actually something very motivated by practical application and also real difficult problem of deriving specifications for that domain, just theoretically interesting. So I really enjoyed working on this project. It was a recent project, but I don't want to talk about it here because it hasn't been published yet. So I'm going to talk about these two things: implementing symbolic operations, and at the end I'll mention some interesting things about the logic. Okay, so I'm going to define the basic symbolic operation first. These are called symbolic concretization and abstraction, the basic building blocks in the previous slide. And then I'll describe two algorithms for computing symbolic abstraction. So going again to the definitions, in the abstract interpretation setting, we have the concrete world and the abstract domain. And for every value in the abstract domain, the concretization function gamma defines a set of concrete states. And there is also an abstraction function which takes a concrete set and defines the most precise abstract value for it. So the most precise means that if I take, most precise abstract value which over-approximates this set of states. And the most precise means that if I take another abstract value which also represents all the concrete states in X, then it will be a superset of the gamma of A1. Yeah?
Maybe the case if does not exist a most precise abstraction, for instance, with polyhedra or other things, it's important for you, this stuff?
Let's assume for now that I need this restriction, and we can talk later about what happens in polyhedra. For the domains I looked at, it exists. So alpha is defined. Okay, so alpha gives me the most precise representation of the set X in the domain. And now I'm going to define the symbolic operations, the basic symbolic operations, to be the counterparts of alpha and gamma. So if gamma takes from abstract domain to a set of concrete states, then gamma hat, the symbolic counterpart of gamma, takes abstract value and returns a logical formula in the specification language L. And alpha is vice versa. So what are the requirements? That we have this symbolic domain now in the picture, and we have for every abstract value, we define gamma hat operation, which gives me a formula in this domain, such that this formula represents a set of states, which is exactly gamma of A. So basically, I can now translate abstract value into a formula which captures exactly the same concrete states that are represented by the abstract value. Okay, the other, now this set of states can be infinite because we have infinitely many concrete states, so sets can be infinite. So now if I want to check this, for example, emptiness, I can use gamma hat and a satisfiability checker, for example. So checking if the gamma of A is empty corresponds to checking the satisfiability of this formula, gamma hat of A. Okay, now I can do, I can extract information or check assertions. I can implement this box. Now what does it mean checking this assertion? It means checking that all the concrete states represented by A satisfy the formula. So I can implement it using a validity checker now. Okay, or satisfiability checker if I take the negation of the formula, if it's in the logic, and so on. Basically, a decision procedure. So I have, that's what the implementation of this box was supposed to mean when I showed it earlier. Maybe it wasn't clear. So I simply translate each operation here into logical operations or alpha and gamma. Okay. How difficult is it to come up with gamma hat operation for a given domain? So it's actually quite easy usually. All the domains I looked at, it was possible to define gamma hat operation, sometimes not very immediate, but it was possible. And usually the formula that we get for each abstract value is linear in the size of the abstract value or something like that. It's not, the formulas are not too big. But of course, it depends on how expressive the logic L that we choose, how expressive it is. So let me show you just some intuitive examples. First is very basic, the constant propagation domain. We have an abstract value maps variables to constant values or top. So here this one says that x has the constant value 0, z is known to be constant 3, and y is top. We don't know if it's constant or not. So gamma hat for that will just take this formula, where y doesn't appear at all. It means that this formula doesn't constrain y, which corresponds to the fact that y maps to top. We have no information about the value of y. Okay? Another example would be predicate abstraction, which is also quite straightforward. Here we have a fixed set of predicates, phi1 to phi n, and an abstract value is a vector of valuations for these predicates. So we can define gamma for that by taking conjunction of all the predicates for which the value is true and the negation of all the predicates for which it's false. So it's the usual thing that I guess all predicate abstractions do. Okay, now here is another, yeah.
I missed one point. So why you do not want to check in the abstract that an element is bottom in that for cost? Can you go to the previous slide?
One before that?
Yeah.
Yeah.
Even before, sorry.
Sure.
So here you are checking if it is empty in the concrete, but you can check if A is bottom in the most abstract.
Because maybe you have several abstract values which represent the empty set of states. And it's difficult to check using the representation of abstract value. It may be difficult to check if the set is empty.
It's a representation, not of semantics.
No. It's a matter of representation, yes. So, for example, for canonical abstraction, it's very difficult to have your shape graph, and then, well, I don't know how many people are familiar here. I'm not assuming any prior knowledge of canonical abstraction, but it's an example where you have a shape graph which encodes part of the information and additional constraints, which if you put them together, then the value may be unsatisfiable. Okay.
So, just going in the analysis, so you never need to check if some path is bottom, essentially. You just need when you want to check assertion. Oh,
Yes.
we can talk it offline, so okay. Let's figure out how it
No,
works.
no,
You
that's
analyze.
fine.
Okay, thank you.
Okay, so just roll it all forward. Okay, so the third example of symbolic concretization is for canonical abstraction. I'm not assuming any knowledge of canonical abstraction. I know some are experts here, some are maybe less familiar. I'm going to use canonical abstraction as my running example, but it will be really just for I'll explain all what I need for that example. So canonical abstraction is can be used for many things, but it was designed to reason about a heap, to reason about data structures allocated in the heap, and it's a very precise abstraction for reasoning about things like that. So the idea is that every abstract value in this domain represents a set of memory configurations. So this shape graph represents a set of memory configurations, each of which contains exactly one linked list pointed to by X and no garbage. Now gamma hat for this abstraction will just encode into formula what I said in words now. So it will write this horrible formula, which means that every memory configuration contains at least 2 nodes and no garbage, and so on. It encodes this shape of this heap. You don't need to understand the details. What is important about it is that we use this n star here to talk about reachability. So we have this shape graph, and it's, the meaning of it is that all the nodes are reachable from X. That I can write it using transitive closure. So for canonical abstraction, we can write gamma hat formulas, but they will be in a very expressive logic, first order with transitive closure. And it makes a difference if we want to have a satisfiability checker. So this abstraction is very expressive, and also it's the corresponding logic needs to be very strong. Okay. Moving on to the second basic operation, the symbolic abstraction. So here we have a formula which represents this set of states, and we want to compute an abstract value for it such that it's exactly the alpha of this set. So it's the most precise abstract value which captures all the concrete states represented by phi. And now what Tom pointed out, if this language is much more expressive, then maybe by moving from phi1 to A1, we lose information, or we represent now in A1 more states than we used to represent in this set. Because this set of concrete states is not expressible. But the idea is to find the most precise representation for it, which is expressible in the abstract domain. Okay, so now to summarize these definitions, we have the usual gamma and alpha, and we have the symbolic gamma, which takes us to the symbolic domain, specification language, and the usual alpha. Now gamma hat is, the symbolic alpha hat. Gamma hat is easy. I showed you examples. It was not very difficult to come up with those. Now, using both of these combinations, we can implement various operations that I already mentioned before, so I'll just go briefly. The assertions I showed how we can implement. Assume we can implement it by taking gamma hat of A. Now we have a formula which represents the set of states for A, and conjoin it with phi by restricting the set to only those that satisfy phi, and then use alpha hat operation to find the most precise representation of that set in the abstract domain. So these two are useful for modular analysis, and we can also implement best transformer and domain change. Domain change is nice, it's easy. Just take A, translate it to a formula using the gamma hat for domain A, and then use the alpha hat for domain B. Okay?
The projection is at the abstract.
So this projection, it's not the projection which requires quantifier elimination. This can be done by just looking at the abstract value, which is a pair. I didn't want to go into these details, but I can.
The abstract domain, not on the formula.
This one is not on the formula. This one is on the abstract domain. So here, okay, let me just explain if we are already at it. This T hat would be the formula which describes the effect of the statement T. So this formula speaks about the state before and after. So when we compute alpha hat, we get pairs of states or some abstraction of pairs of states, and then we take out, depending on the representation. We might also be using different abstraction for sets, for set of pairs of states, for the relation on states, and then it may be not trivial to implement. But usually for the things I looked at, it's very easy to distinguish the state before and after when looking at the abstract domain. Okay. Okay. Yeah.
So the sum operation is really just a special case of the next.
Yeah. So I was actually cheating when I showed the modular analysis example, because I should have used projection of assume there, because the post condition for append also speaks about two states. Okay, but it's easier to explain it this way at the intuitive level. It's also not an important, like it's important, but it's not a theoretically difficult thing to implement. So there is no hidden problems, I hope, not as far as I know.
Just a question about, I guess you have an implementation of all of this.
We implemented.
Yeah, for the assumption.
We implemented it for canonical abstraction.
So when you do the assumption, you really use this formula, or you computed the assumption by hand, so to be more precise? You can just do the abstraction of A and then do the meet in the abstract. You can use another approximation, or you just use this machine. It can be very expensive going to the concrete, doing the step.
Oh, okay. We cannot. Sorry, we cannot go to.
My question is for a particular abstract domain, fixed and abstract domain, so the one in your implementation. Do you use this definition that it seems to me expensive, or you implement it by hand and just saying this is the assumption? Just.
Are you talking about the implementation of alpha hat?
Alpha and gamma, and all the assume operation.
So assume is composed of these operations, and I implemented just like I'm showing here by using gamma hat and alpha hat.
But if you want, you can expand and maybe another approximation or something.
Maybe there are other ways. Okay. Maybe there are other ways to implement it. So I'm going to talk now about how I'm implementing alpha hat. So gamma hat is easy. I showed some examples, and it is. And alpha hat is more complicated. So why is it? The reason is that in alpha hat we are going from specifications which are more expressive to something less expressive. We mentioned it. We talked before. Another kind of usual question. It's easy to compute alpha, the abstraction function, for a single state, for example. Given a state, I can easily compute its abstraction. Why implementing the symbolic version is difficult? So the reason is that just this set is infinite, so I cannot go one by one and abstract them and take join. Okay? And a naive algorithm for implementing alpha hat, if we have a finite domain, would be just by enumeration. So we can go over all possible values, abstract values in this finite domain, and for each of them check if it represents all the states in phi or not. And if it does, then we collect it and then find the least such element. Okay, that would be a naive implementation. Now, even if we are talking only about the finite domain, they are very large. At least I'm interested in domain is double exponential. I don't want to be enumerating. I want to save some time and do some better things. But already here, we see the difficulties. So already, even if we want to implement the naive algorithm, we already know that we need the gamma hat operation and we need a validity checker. Okay, so these requirements are already here. And if L is very expressive and the validity checker sometimes is inconclusive, sometimes diverges and times out, I can always implement a sound version of this algorithm by giving an answer which is not the most precise representation of the sets defined by phi. Okay, so that would be a sound but not precise answer. So now I'm going to show two algorithms for computing alpha hat which are not naive. And if all the conditions hold, if all the calls to the theorem prover that I'm using, if they are all conclusive, then the result is the most precise. So the first algorithm works from below. It starts from bottom as an approximation for the final result of alpha hat, and it works its way up the abstract domain using some process of successive approximations. And the other algorithm starts from above and works its way down the abstract domain using a completely different technique on each step. If this abstract domain has a unique fixed point, then both will find the same result. Okay? So, yeah.
What is a unique fixed point?
So if the greatest fixed point and the least fixed point are the same in the
alpha.
abstract domain, then if we start from bottom and from top, we'll reach the same thing, assuming that all the reasoning here about the formulas was conclusive.
So you say that the algorithm from below computes an over-approximation of the least fixed point?
From below computes an under-approximation, from above computes an over-approximation of the least fixed point.
But does the above compute a greatest fixed point?
Yeah.
Or a precise greatest fixed point?
So first of all, I'll talk about it, but the one from above that we have currently, it works for canonical abstraction, and there the domain is finite and it's unique fixed point. But in general, we are now thinking of how to extend it to any domain. I mean, we have some ideas, and then it will compute the greatest fixed point. So kind of generalization of what we currently have in the Takas paper would compute the greatest fixed point if it's not unique. Does that answer your question?
If the domain is so infinite 8 and it computes a greatest fixed point, then the alpha that you obtain is an over approximation of the alpha. It's not the most precise.
Yes.
Okay.
If that the VMKI algorithm works for finite height domains, I was planning to say it later, but if it raises a question, I can also say it now. So the VMKI algorithm works for any domain with a finite height, and if the height of the domain is infinite, then we can use widening to guarantee the termination, and then we lose the precision, of course. And the Takas algorithm works from above, and it's only for canonical abstraction at the moment, as it is in the Takas paper. Okay, should I continue? Going back to the example that I showed you earlier. Okay, so I just want to show you how alpha from above works and alpha from below works on a very simple example. So I'm going to take this precondition, acyclic, and create this abstract value A0. So it would be just computing alpha hat of acyclic Z. And acyclic Z is an assertion which says that Z points to an acyclic linked list. And this abstract value looks like that. You don't need to understand much, but those who know about canonical abstraction, this is the list reachable from Z, and this is the garbage, because this assertion doesn't say that there is no garbage, okay? So I'm going to show the algorithm from below first. I think it's a cute algorithm. So the idea is to start from bottom as an approximation for the result of the algorithm, and take the formula acyclic Z and check if it's satisfiable or not. In this case, it is satisfiable, no problem. And then we ask the satisfiability checker to provide us with a concrete state or a concrete model on which this formula is satisfiable. So it will return some model here, for example, this one, which represents list of length 3 pointed to by Z. Now we compute abstraction of this state and get some abstract value over here, which is this one, for example. Abstraction is easy to compute for one state. So we just look at the state and merge all the nodes that we don't want to distinguish between, and we get this abstract value. Anyway, now we have this abstract value. We update our result to be this new abstract value, and it corresponds to covering some set of states in the concrete world, which is larger than the initial state, because now this abstract value represents all linked lists of length 2 or more pointed to by Z. And this was just one of them. So we applied abstraction. We used alpha to generalize from one concrete state to more states. Okay, now I can write this formula here, which means give me all the states that satisfy the assertion, the original assertion, that are not yet already represented by the abstract value that I have here. Okay, so it represents all the other states in the circle which are not yellow. And then I start a new iteration of this algorithm. Again, I look at this formula, I ask the satisfiability checker, is it satisfiable? And if yes, please give me a model. And it gives me a new model for this formula, in which we have list of length 2 pointed by z and some garbage elements. Okay, I use the same trick, I apply abstraction. Now I get this abstract value, and I join it with what I had before, and get this graph. Okay, this is my new result for alpha, still under approximation, and still hasn't covered everything. It still hasn't covered everything. It covered some more. So we continue this way until we reach the value we're looking for, which is this one. Yep.
You can join any of these two shape graphs, right?
Yes.
But you don't always get a shape graph. You can sometimes, or do you?
So these shape graphs are abstract values in the domain, in the abstract domain that I'm using. So if I take join of two abstract values, I can always compute a join. I can always find an element in the abstract domain, but it's possible that by joining, I also lose information. Okay? So there are two sources in which I generalize. One is by alpha and another by join. But this is pretty standard, I suppose. Okay, so to recap on the algorithm from below, it starts from bottom and covers more and more states. What drives this process are concrete states and abstraction of concrete states, and until we cover the whole thing. Okay, now this is how alpha from below works. As I said, it applies to finite height domains, and it requires a satisfiability checker and a model generation. Now, one thing to note here is that the algorithm, the way it works, it operates from below. So the intermediate result that we have at any program point, at any point of the analysis, does not cover all states in phi. There is a state in phi which is not covered. Otherwise, the satisfiability check would say unsatisfiable, and we're done. Okay, so at any point we are below the result that we want to compute, and if we cannot return the intermediate result, it's not useful. It's unsound for our analysis. Maybe it's useful for other tools. I haven't thought about it. Yeah.
So in your implementation, which theorem prover did you use?
Sorry?
Did you use a theorem prover?
So here I'm assuming that the satisfiability checker and model generator succeed. Okay? If they failed, and I'll mention it, then I cannot guarantee precision anymore.
Are you going to mention the theorem prover that you used for your specific shape graph?
Oh, if I have time, I'll say a few words about the theorem prover for shape graphs, or the decision procedure that we have. Okay, but I hope.
So finite domain
If not-
A. If it's not finite height, then you need widening.
Yes. But if I use widening, then the result is I cannot guarantee precision. Okay. Okay. So this is a disadvantage of this approach, and to address it, we came up with the algorithm which works from above, in which we can stop at any point, and we have something which is sound, and we can return. Maybe it's not very useful, but still, if the height of the domain is it's finite but very large, then maybe we want a timeout or something like that. So, okay, the way the one from above, yeah.
Can you go back?
Sure.
So then, is that also for finite height domains or no? Or
So the algorithm described in the Takas paper works only for canonical abstraction. It's specific for canonical abstraction, although canonical abstraction is what we were interested in at that moment. And now we're working on an algorithm for a general one which works from above, which works for more domains. So it's an ongoing work.
including polyhedra?
No, for finite height domain, let's say. Actually, the question is, what are the requirements on the domain? So we're trying to understand the requirements by looking at the intuition that we have from this algorithm. And I'd like to show one step of it just to give them.
But it's something like narrowing, right? Because you're starting with top, which is way too over-approximate. So it should be something like a narrowing, which can be precise for certain.
Yeah, but in some smart way, which uses the shape of the abstract domain, because we can always, start with everything and then just check the naive algorithm for validity. Okay.
So, have you combined the above and below complement each other?
That would be interesting. I haven't thought about it. I haven't thought.
It's been pursued.
Okay, that would be very interesting, but no, not there yet. Okay, so the one from above starts from top, which corresponds to covering all states in the world, and then works its way down the abstract domain, which corresponds to refining the coverage until we reach the most precise set, which over-approximates V. Okay, so I'd like to show you just one step of this process which works from above. It's very simple example. So this is the final result that we get in this example for a cyclic of Z for this property. That's what we get also from the algorithm from below. Suppose that we work from above and we reach this A1, which looks like that, which covers some over-approximation of the states we want. Okay, so now I'm going to show just one step from this abstract value. In this step, so the idea of each step actually is to look at the may information which is present in the abstract value and try to refine it. In the case of canonical abstraction, here the may information are the dashed edges, which we don't know if there is an edge or if there is no edge. So in this step that I'm going to show, I'll concentrate on this red edge, which goes from node U2 to U1. And try to refine to see if it's a necessary edge or not. What does it mean necessary, if it needs to be there? It means that there exists a node represented by the summary node U2 with an edge back to the node pointed to by Z. Okay? If there exists one concrete node represented by this one with an edge backwards, then we cannot remove the may edge. And we can define this condition as a formula and take it together with the definition with gamma hat of this abstract value and the original condition, construct this formula and ask if it's satisfiable or not. Okay. So in this case, it's not satisfiable, because the formula phi says that the list Z is acyclic, and if there exists an element represented by this node with a pointer back to Z, and every element that is in this node is reachable from Z, then we get a cycle. So the answer that we get is no. So we know, okay, this may edge can be removed. So just remove this may edge. And it corresponds to, over here, to refining the over-approximation of the states that we have. Okay, so we continue this way. It's not the final result, because here some instrumentation predicates are still 1/2, until we get this abstract value at the end of the process. Okay, so the idea of the algorithm which works from above is to look at those may bits that are in our abstract value and try to check if they should be may, remain as may bits, or can be refined to something more precise. If there is some may information which is a clear over-approximation of what we want to represent.
So is the abstract domain an automaton in your case, or in this example?
Abstract value, you mean?
Your shape graph. Should I read it as an automaton?
So the way we define it can be probably thought of as an automaton. The way we define it, it's a logical structure, free-valued logical structure. And because it's a logical structure with only binary relations, we can draw it as a graph.
And then you want to get from one logical structure to the other by strengthening it.
Yes.
So in this example, you say you can strengthen it by removing an edge or removing some annotation. But wouldn't you also have to add states?
Aha, okay, so maybe your question is, how did you get from your representation of top to this guy, which has 3 states? So I wanted to show only the simple intuitive step of how we do the refinement. There is another kind of main information, which are these summary nodes. So if we start with one summary node, refining this main information means splitting nodes, bifurcating the nodes. So there are different kinds of this refinement.
So it just occurred to me, with this framework, you should be able to combine this with abstraction refinement so that you don't need to necessarily compute the most precise abstraction. You can do some fixed point. If you find an error, you can use your whole technique to actually figure out where to sort of do the refinement. So you don't necessarily need to go all the way down.
Yeah, this could be an interesting strategy of refinement. I haven't, again, thought about this. Yes?
This May edge, its May status is the third value in your logic.
Yes, so when I had it in red, it was the May edge for which I didn't know if it should be there or not. But after I checked it with this satisfiability, it has another meaning. It has meaning which says, yes, it's a May information, but it cannot be refined. So it corresponds to one of the interpretations that we have for the value 1/2 in the canonical abstraction. We sometimes use one interpretation, sometimes another, and here I use both without going into details. Okay, just 1 second. So for the question that that was asked here, this is not a shape. This is not an automaton, but it can be thought as an automaton. There are works that represent heaps using automata, also. Yeah.
Very general. So I want to just ask you a simple question. Is this domain of shape graph finite in the height?
It's a finite domain. It's finite height and finite width for a given set of predicates. So it's parametric like predicate abstraction is.
If you're interested only in reachability properties of the shape graph, why not simply use temporal logic?
Because temporal logic cannot talk about equality, so I'm also interested in properties like aliasing and sharing.
But you can abstract that using some predicates, using the annotation, additional proposition. So for a reachability part, you use temporal logic, and for that other part, you use some predicates that assign atomic proposition, and then you take that. That would not work?
I think it might work. One of the difficulties is how do we check satisfiability of such combinations. And from what I learned, like I wanted to talk about it in the second part of the talk, but we probably don't have time. When we have reachability properties and equality in the same logic, the reasoning becomes very difficult. So have to limit other parts. And in mu calculus, we know it's decidable, exponential, time, because there is no equality. That's why it's so easy. So easy.
Yes,
So to speak.
and I mean, in all this with the May and the refinement, etc. You have like 3-value temporal logic, which is there's like refinement on these model transition systems, etc. So you have very nice results there, which make the picture really nice. And but it's more restricted than here. But
Right.
I wonder, how much can you reuse of these results, or I just don't understand. Okay, but we can take that offline.
So a high-level answer to that there are two things that are really important for shape analysis. One is the reachability, another is sharing, and we cannot express sharing in mu calculus and such. So it's good for some things, but maybe not for all the things. And the logic, the decidable logic which we found expresses both. So it will probably remain as an advertisement. I don't know how much time I have. Okay. So just to summarize, we have two algorithms for computing alpha hat. And one works from below, and its intermediate results are not sound, and it also requires a model generator. Here we don't need a model generator, we only need satisfiability checker, and it works from above. There are different trade-offs. Extension to infinite high domain, I mentioned. If the satisfiability checker or model generation fails, we can always come up with an approximation to guarantee soundness, but we might lose precision. And of course, I don't mean here like this naive over approximation, just return top. There are, other things that we can do. I don't have time to go into this. Yes.
So if the logic is decidable, and you have the finite highest abstract domain, couldn't a decision procedure within the abstract domain just compute the reference?
If the logic is decidable and the domain is finite, then the naive algorithm would work, or any of these algorithms will also work. Okay, so if inconclusive, then we lose precision. Now, one of the problems of these algorithms is that they make many calls, repeated calls to satisfiability checker. Sometimes the difference between two input formulas is not so much, so there is a lot of opportunity to reuse within satisfiability checker tools, but there are no tools that, at the moment, as far as I know, which support such warm start or shared queries. I mean, there is the decision procedure that Shuvendo and Byron and Tom, I suppose, worked on it, but it's not sufficiently expressive for shape analysis, for example. So one way to address this large number of queries would be to use concrete execution. So the idea is that if we use the algorithm from below, every time the model generator returns a model, what I showed you, we abstract from the model and forget the model. What we suggest in ISTA paper is to keep the model, to run the program on it, and use it to compute more abstract values. So I don't want to go into the details of that, but this is a very cute extension and generalization. The real question is, how do we choose a good specification language, which on one hand is expressive enough, and here by expressive I mean that it can encode all the assertions that we want to check. It can encode all abstract values so that gamma hat is defined. And in addition to that, the alpha hat algorithm uses more general formulas. Like, for example, in the alpha hat from above, we take phi and the negation of gamma hat. So this specification language should be able to express negation. That's about expressivity on one hand. On the other hand, automatic reasoning is important because this algorithm makes so many queries to the theorem prover. We just cannot ask the user on every query to help us. So we need a satisfiability and validity checker, and also a model generator for alpha hat. So from below. So the algorithm which works from below, it has this additional requirement on model generation. But on the other hand, with the ISTA extension, with the extension which uses models to reduce numbers of calls, it's not clear which is better. In any case, we would like such satisfiability checker to be predictable, in the sense that if we call it and it cannot come back with a conclusive answer, it tells me that it cannot come back with a conclusive answer. It just doesn't. It shouldn't tell me satisfiable whenever it cannot prove unsatisfiable, so that I know when exactly I'm losing precision, when I need to do something about it, or not. Or, like, for example, a timeout is a good thing because I know that my timeout fired. I know that I lost precision, or potentially lost precision there. So predictability is good. One way to get predictability is by using a decidable logic. It's not necessary to use a decidable logic, but it's something which gives this predictability. And this sort of drives me to the second part of the talk about the logic of reachable patterns. Unfortunately, I don't have enough time to talk about it. I'll just mention like in a few words what it's all about, and then summarize. Maybe I don't have time even for that. So when reasoning about heap manipulating programs, as I already mentioned, it's important to be able to express reachability, and it's nice to have logic which is decidable in order to be able to incorporate it in program analysis tools. But reachability and decidability are very difficult together, very difficult to achieve together. It requires giving up on something, either talking about simpler properties of general structures or simple structures such as trees, and talking about expressive properties such as monadic second-order logic. So in this work that I wanted to talk here about, and I don't have time, we developed a logic which is called logic of reachable patterns. It's very nice. It's very natural, I think, to describe various properties about recursive data structures. It allows us talking about all the things we want to talk about, many of the things we want to talk about, and it doesn't limit, for example, number of binary relations and so on. It's closed under negation, so it's very useful for both validity and satisfiability and other more complex queries. It has finite model property, which is strong because we're only interested in finite models. It has a bounded model property. Sometimes people call it small model property, but in our case it's not small, it's big, but it's bounded. And it's decidable. The proof of decidability is, I think, not trivial. It wasn't trivial to me. It uses some version of a generalized tree model property or tree-like property. It's not, the model is not a tree, but it's close enough to tree that we can reduce the satisfiability of these formulas to satisfiability of MSO on trees. And this logic is useful for verification. Okay, so I promised.
There's a way to just say what is the bounded model property. What is the bound?
Double exponential.
Double exponential?
Yes.
It's not non-elementary.
It's not non-elementary like an MSO on trees because we limit the quantifier alternations. The non-elementary bound comes from quantifier alternations, and here we have no quantifier alternations. One of the ways to carefully design the logic to be decidable is to give up on quantifier alternations. Okay, so I promised an example which shows how post is defined, but I don't have time to explain it. Just want to point out that we use two vocabularies. N describes the value of n before the call to append, and n prime, the field n prime, describes the values after append. And we can say for the post condition that from A we can reach the last element, and what makes it last is the fact that from there we go directly to null. And after the procedure runs from last using n prime, the new value of n will go to B. Maybe I can show it later.
So the second precondition is saying that A and B are disjoint.
Yes.
So you can express separation in your logic naturally.
Separation, as in separation logic.
Yes.
I can often express similar things in a completely different way.
Okay.
Including separation, I would use this predicate for disjointness. But the intuition is different than in separation logic because most of the constraints here are global. And there, the idea of separation is to have local constraints for which if you combine them, or if you take a larger heap, they still hold on it. And here we cannot do that because reachability is kind of crosses the subheaps from one to the other. I don't know.
So can you tell me what the second but last thing?
Okay, yeah. So in this formula, the last part over here, it defines the preserve information from the of the method append. So this one says that everything that is reachable from A by following n pointers, the n and n prime is the same. So here is the definition. Same is a predicate. It's a pattern. And our logic is called logic of reachable patterns because of the ability to write these patterns. So, and this one says that from B, everything that is reachable by n, every node that is reachable by n has n and n prime pointing to the same thing. So the last two lines are just the preserve of append. Okay? So we can do verification using LRP if we have sorry.
So you respect there. So last first of all, I guess it's essentially quantified over that formula, I guess, right? But you're not saying anything about the result and your verification.
It does not. I don't say anything about the return value, but x. Where is it? The A remains the same before and after the procedure call because the semantics of programming language cannot change in visible variables. Suppose that A is local of the caller. So.
But when you use the post condition in your examples, you said x gets append of some arguments.
Yes. And this is okay. I could probably model it by giving a new value for x using x prime. Yes. Well, you're right. Maybe there is some mismatch between
Like you would have needed that for the verification that the slides suggested that you had done. But
yes, it would be very easy to define. Actually, I would just write here. I would add in this post condition that result equals A. Okay.
And one more question about the same n and prime. That says that in the formula that appears to the left, you want to compare all of the things with n with the same things where n has been replaced by n prime. Is that right?
Are you talking about this one?
Right.
The one before the last?
Either one.
Either. Okay. So the semantics of this formula is that everything that is reachable in the heap from the node pointed to by B using n fields is defined, satisfies this pattern. And this pattern is first order quantifier free logic formula, which says that if I have an n edge from V0 to V1, then there is an n prime from... Okay, it's a typo. I'm sorry. Oh, it's reversed. Sorry, maybe the typo is confusing.
So that same is now. So now you've defined it down there to be a predicate. And what is the role of when you write B square brackets of something? What does that return?
Oh, this has true or false.
Right.
So
and
it's
what about the same thing is a predicate and it happens to be that predicate.
Yes.
Modular the top of the typo. And what's the left part? I mean the B and square brackets. What does that return? A set of elements or
no, it's a proposition. So this LRP, logic of reachable patterns, it's a propositional logic. Boolean combinations of reachability of constraints of this kind, of this form. So each constraint is just true or false, evaluates to true or false on a given heap.
But when you say the modal box, the square brackets.
Yeah, it's inspired by the box and diamond of the modal logic and supposed to be intuitive, but I guess for the box it's not very intuitive.
So it's almost as if that we should move on. Okay.
It says must to be the same.
Sorry?
Must to be the same.
for any path.
It same takes care of the sharing that you were talking about in some sense before, right?
So
And the boxes are like temporal logic operators, so it's like an additional predicate for the sharing and then temporal logic, roughly. No?
yes, but the interpretation of same is also part of the logic. So in the well, actually here same doesn't use any equality, but there are additional constraints I didn't show, which say that n is a partial function, that there is only one outgoing n edge for every node, and there I use equality, and also to, for example, to say that I can say that the output list is unshared or other things. So. But we were hoping, it's very related to model logics, in fact. Okay, so we can generate verification conditions in LRP if the pre and post conditions are in LRP. We can do modular analysis if we can define gamma hat in LRP for abstract domain, and for a certain set of instrumentation predicates for canonical abstraction we can do that. And this is like more future work. It's decidable and has a non-trivial model property. I'll skip that, and I'll skip some related work about MSO. I mentioned it earlier. MSO on trees is another way to get the decidable logic with reachability. Although MSO on trees is not expressive enough for our needs. Here are some related work. One of this is model logic. The interesting thing is the description logic. So the inspiration for LRP was shape analysis or reasoning about data structures, and then it turned out that it can be considered as another description logic. And description logics are useful in this very, hot area of semantic web. So I'm trying to figure out how exactly this is related. So if there are people who know about it or can educate me, I'd be happy to learn. To summarize, LRP is a surprise. It's useful and decidable logic. It's not easy to find such. So the principles that allow us to define a decidable logic are basically talking about arbitrary structure of the heap, not restricting the number of binary relations, because it's important for us to write formulas in this logic, and with restrictions on number of binary relations, we're in trouble usually. Another important thing is no alternations of quantifiers. This restriction gives us a lot of flexibility in other uses in other expressive components of the logic, such as reachability. And finally, syntactic limitation on the pattern. So we have some maybe quite ad hoc restrictions on the way patterns should be written for this logic to be decidable. But these syntactic restrictions actually come from our understanding of the model property. And whenever I want to extend the logic because I find something which is not expressible in that logic, I just look at the proof, and well, it often happens. Then the proof just works for the extended, for the new property, which does not satisfy the syntactic restrictions. So the core insight from working on this logic is this understanding of the model property. It says that if the formula is satisfiable, then it is satisfiable by a model which is very close to be a tree. And that helps a lot. It's not a tree. We still allow cycles, even unbounded number of cycles, but we can easily convert every model to a model which is very close to tree. So to summarize, I presented two algorithms for implementing symbolic abstraction, and unfortunately didn't have time to talk about the logic. These two works are part of my thesis, and I was involved in additional projects here with Madan as well, and in Tel Aviv University. And now there are some works that I mentioned briefly during the talk. One of them is implementing an actual decision procedure for LLP. So I implemented some naive decision procedure, and it used translation to Mona, and I tried to optimize the translation, but I didn't manage to make it work well enough for what I wanted, or for large enough formulas. So currently I'm looking at different approaches I'm not an expert for that, so I'd also love to learn to get some feedback from you. That modular type state work, and now new work on I'm learning about separation logic. So that's what I wanted to say, and I mentioned most of these things already. And just to summarize, I think that there is a lot more to do in combining these two fields: automatic reasoning about programs and automatic reasoning about logical formulas. There are a lot of interesting and useful tools on both sides, and there has been a lot of work on combining these two, like since forever. But I still think that there is more to do. So that's what I wanted to talk about.